Hello and welcome. This presentation is a live demonstration of our SLIM software for the Configurable UAV Challenge hosted at the INCOSE International Workshop in Torrance, California in Jan 2015. My name is Manas Bajaj and I represent Intercax. I will be your presenter. This is the story of Sam. Sam is a very smart and experienced system engineer at a company called Get Your UAV that is designing a next-generation configurable UAV platform. The platform will be the basis for developing UAVs for different missions such as surveillance, search and rescue, and agricultural missions. Sam will be working with a diverse group of engineers across multiple partners that are geographically distributed. In this project, Sam wishes to focus more on the systems engineering problem at hand and the modeling and simulation of the UAV platform and its variants, rather than communicating and reconciling models between different engineering disciplines and tools. Sam does not want to use documents for exchanging vital systems engineering information. Sam's current system engineering environment looks something like this. He and his team have been using documents, spreadsheets, drawings, etc. to manage their system architecture. At Sam's own company, they use Siemens Teamcenter as a primary PLM system where the details of the UAV that they design and integrate with is managed. Sam's company also works with a platform maker, in this case the company is called Platforms Inc., that is using PTC Windchill for developing the core platform of the UAV. Sam's company also works with another partner called Instruments LLC that provides the payload instruments, the thermal cameras, the video cameras, the radars, and other instruments that form the payload of the UAV. Within Sam's own company, they use several detailed design analysis and simulation tools, for example, Siemens NX, PTC Creo, and Simulink. The communication between the system architecture models and the different PLM system models and design and simulation models and databases has often been very document centric. Files exported from one tool sent to another tool in a manual or a semi-automated manner, and that often causes discrepancy in the overall architecture of the system and in the individual models in these different tools and domains as the entire ecosystem of model evolves over time. Sam wishes to change that this time. He has been working with our company and has taken our SysML training and has learned about modeling complex systems using SysML language. This time he wants to use SysML as a way of capturing the overall architecture of the system and wants to use our SLIM product to be able to communicate and maintain connections between that architecture and the different detailed design and simulation models, whether it's the PLM systems or the NX CAD systems or the Creo CAD system or the Simulink models and so on. He also wishes to connect the system architecture models to the payload database from where he can actually exchange vital payload information. In addition to SLIM, Sam would also use Paramagic for performing parametric simulations on the architecture from the very initial stages of the design and learn about key performance estimates and other aspects of the system so that he can refine them as he moves along. So this is how Sam's story would go. At the first step, Sam would define the configurable UAV platform system in SysML, its requirements and its initial block structure. Then he would push these requirements to Teamcenter, where Teamcenter would start managing the complete set of requirements for the UAV. At the next step, Sam would develop a variant architecture of the configurable UAV using the UAV platform definition that's coming from the Windchill repository of one of his partners and the payload instruments that are coming from the MySQL databases of the other partner. Then he would perform a parametric analysis to compute key performance measures of the UAV, for example, the range, the endurance, and the max velocity. At the next stage, Sam would then dive into the detailed design and analysis part of his model development. He would seed a Simulink model of one of the UAV subsystems, in this case the gas turbine, from SysML for detailed simulation. He would also seed an NX CAD model of the UAV payload and the instrument volumes from SysML for detailed design. He would then push the configurable UAV variant architecture to Teamcenter for further development. And at the end, Sam will visualize the total system model federation, how the architecture model in SysML is connected to a very wide set of repositories and tools, and what is happening at those connections. So let us move on to a live demonstration of Sam's story. At this stage, we will move to Magic Draw. And again, we're using Magic Draw as a representative SysML modeling tool for our demonstration. You could as well use IBM Rational Rhapsody that works with Slim. Moving on, the first thing that Sam has done here is to actually represent the configurable UAV platform itself. Now, Sam is a very smart guy. He feels that before he writes meaningful requirements, he must first define what is the system about which he's going to write requirements for. So in this case, Sam has defined a configurable UAV block that has the platform, which is the core aircraft component of the UAV, defined a software subsystem, which includes both flight software as well as the mission software. Has defined a payload component that includes the different sensors, has defined a communication subsystem, which includes both the line of flight communication, such as with the ground station, as well as the satellite communication. Sam has also defined a set of requirements now that he has thought about the system at hand. In this case, he's defined the cUAV specification and defined range requirements, speed, endurance, and altitude requirements. Has defined payload specification, which has the volume and the mass specifications for the payload. He's got the flight control specification that has got the autonomous and remote operation requirements and the flight communication specification. And he has defined them in quite a bit of detail in a requirements table, as you can see, with all the shall statements in there. Sam has also been able to relate the requirements to this early definition of this configurable UAV platform. For example, the cUAV block satisfies the cUAV specification. The payload component satisfies the payload specification. The platform component satisfies the flight control specification, and so on and so forth. Now let's go ahead and launch the Slim software, which is deployed here as a plugin for Magic Draw. So you right click on the top level model, go to Slim, and launch the dashboard. The first thing you see in the Slim dashboard is the repository manager that shows all the repositories to which Sam has a connection with. In this case, the first thing he does is actually go to the Teamcenter repository of his own company. You can see he's connected to his Teamcenter repository. If he expands the home folder, this makes a live call to the Teamcenter repository that is situated the other part of the United States in our office in Atlanta. And then he goes to the connection manager, where he can see the SysML model on the left hand side and can toggle back and forth between the different PLM systems and databases and other repositories. So he goes back to his Teamcenter repository, expands the home folder, goes to this specific folder called D2, and then goes to the requirements package and then drags the configurable UAV platform specification to this D2 folder. And that way, Sam has now started to generate SysML requirements in Teamcenter, where they will be version tracked and managed and be shared with a larger group of engineers that are working with Teamcenter. Now, with that drag and drop, as you can see, Slim has generated those requirements in Teamcenter. If I expand the configurable UAV specification right here, I can see version A1 has been created. If I expand version A1, I can see that it has a structure and all the child requirements and their versions are also seeded here. What has also happened at the back end is that Slim has now created connections between each of the SysML requirements and their corresponding requirement in Teamcenter. And these connections are at the heart of Slim. Sam will be using these connections to compare and synchronize requirements between SysML and Teamcenter as either changes over time. Now let's move to the next step. After having seeded the requirements from SysML to Teamcenter, Sam now connects to his partner's Windchill repository, where he's been given access to the platform for the UAV. And he expands this one particular product called the UAV platform, expands the part structure, and sees that there's actually a platform that's being designed by the partner, and it's at version A16. If he expands the platform, he can see some of the internal details of that platform part in Windchill. For example, he can see the electrical system, the fuselage, the propulsion, and the wings. At this stage, Sam then drags the platform version A16 to his SysML model, in this case a structure package, and it asks if you want to generate a SysML block structure from the Windchill part structure. He says yes. And it also prompts for what specific properties, what specific attributes from those Windchill parts do we need to bring over to the SysML model, the system architecture model. And in this case, Sam is really interested in tracking the mass of the platform because he's going to use it for mass rollups later on. So he picks up the desired mass and the goal mass of the platform. He clicks OK. And now Slim starts generating a SysML block structure for the platform that represents the actual part structure in Windchill. Now we're not showing it here, but you do have the option of selecting how many levels of the platform structure from Windchill you may want to bring. Because as a system engineer, Sam may be interested only in the first few layers of the platform product in the Windchill repository. Like as before, not only have blocks being generated on the SysML side for the platform, but now there are also connections that Slim is tracking between the block on the SysML side and the corresponding part version on the Windchill side. Now if we go back to our SysML model here, we can expand the structure package, and now we can see that this platform block that was there as part of the configurable UAV architecture now has been tagged as a Windchill part. Now it's linked to a Windchill part version in the Windchill repository. We'll try to expose all the children parts of this platform, and now we can see that it has a lot more detail to it. We see that it has the electrical system, the fuselage, and the propulsion, and the wings that have been brought over from Windchill. And each of those are also blocks defined in our architecture model, such as the electrical system, the fuselage, the jet engine for the propulsion, and the wings, and so on, which are here. Good point to save the model right now. Or you could actually commit it to a teamwork server as well at this point. Now, moving back to Slim, the other aspect that Sam wishes to work with is the actual payload instruments that are being managed by the partner in a MySQL database. In this case, the partner is a company called Instruments LLC, and they are managing the payload systems in a MySQL database. They have given Sam an access to a publishable version of those instruments, and Sam, having access, can expand the instruments database in the MySQL repository. He can see that now it has tables of different video cameras, thermal cameras, and radar systems that he has access to. And Sam, at this point, can expand these tables, or can also do a SQL search right from the repository due to filters and stuff like that. At this point, there are only few instruments here, so he knows the ones that he wants to pick up. So he wants to pick up these two video cameras, two thermal cameras, and these two radars. And he's going to bring them over on to the SysML model and create them as specializations of the table. And so now, as you can see on the left hand side, this has brought over the radar, thermal camera, and the video camera blocks that have been generated from the table, and the entries in the table, the two specific radars, the two specific thermal cameras, and the video cameras that we selected, have been brought over as specializations of these blocks. So at this point, Sam can do a little bit of improvement on his architecture. He's got the radar system here. He's got the thermal system, the thermal camera here. He's got the video camera in here. And now he's going to update his architecture model and say, instead of generic sensors, his payload subsystem actually includes a collection of radars. It includes a collection of thermal cameras. Here we update the multiplicity. And it includes a collection of video cameras. We'll update the multiplicity here as well. As you can see, in a matter of minutes, we have been able to connect the architecture model to two different PLM systems, push requirements from the architecture model to the PLM system, which in this case is also managing the requirements. We've been able to bring the platform component of the UAV from Windchill, that is hosted at one of the partner sites, into the architecture model. And we've also been able to bring in payload instruments from a MySQL database that is being managed by another partner into the architecture as well. Sam at this stage is very happy. Very often, this process has taken him weeks, where these pieces of information have to be exported in different documents and spreadsheets and emailed to Sam or hosted on a server, and Sam has to pull them, make sense out of these pieces of information, and then recreate them as blocks, perhaps in a system model, and connect them. And when things change, he would have a real difficult problem on knowing what has changed and how he would work with that. So let's actually play out that process. What happens when things change? What would Sam do? And how would Slim help him? Well, to mimic that process, I'm actually going to go to Windchill. So we're going to take off Sam's hat and wear the hat of the platform maker that is working on their Windchill PLM system. And they have the platform at version A16 that you have seen here. What they do is they actually go ahead and add another component to that platform design. In this case, they are going to add a landing gear part to that platform. Now, a landing gear has already been defined before. It has just been brought into the platform. They're going to give a name to the reference designator here, landing gear. And then go ahead and check in that part. Now, Sam comes to work and says, well, I really need to figure out if things have changed on the structure side, on the requirement side, and so on. So what he can do with Slim is that he can actually right-click on any package and then hit a compare menu here. And that would start comparing the SysML model elements and their connected PLM or database elements for all the packages in this model. In the interest of time, he's going to just do it for the structure so he can see if things have changed on the instruments database or on the Windchill system. At this point, he right-clicks on the structure package and hits compare SysML and target. And that goes through a process of comparing the models on both sides. This will take a few seconds. This is happening real live with a live database and a live PLM system. And as he says that everything else is fine except for that platform, which is now at version A17, as we can rightly see here in the PLM system. But the SysML model has the platform block that is connected currently to version A16, but A17 is the latest. And the difference is that landing gear that has been added on the platform side. And at this point, Sam just wishes to synchronize that, so he can go to the structure package. Again, he can perform the sync operation at this package level, or he can actually go to the platform and just say sync target to SysML. And in that case, if you refresh, the platform is now block is now linked to platform version A17 on the Windchill side. So now he can also see that that landing gear part has been brought in, and the platform on the SysML side has landing gear. Now that makes Sam's life really easy, right? He can actually do these compare operations at the different package levels and know what has changed and what's going forward. In the current version of Slim, it's purely a pull operation where Sam is deciding when he wants to compare, when he wants to synchronize, and so on. But in the future versions of Slim, we want to make this process a lot more automated with notifications and make it more of a push-based process, very similar to how we see it on our smartphones when you have an email or a message that the phone informs you about. So that's the mode it'll mature into. In a similar manner, Sam can also do compare and sync operations for requirements that are being managed in his Teamcenter repository, and he just did this for both the PLM system, in this case Windchill, as well as the MySQL database, and nothing had changed on the database side. But if things were to change, Slim would have detected that change and then helped Sam to compare and synchronize. When you're trying to push changes from the SysML model to the PLM system, at that point, Sam would have had different ways of dealing with it. If he had the privileges to change the part on the PLM system, he could have done that, or perhaps issued a change request on the PLM system. All right, at this stage, Sam would like to move to the next stage of his model development. He's defined a system architecture model here. He wants to dive into analysis. And for this, let's get to stage 2, where Sam has actually defined a parametric model, a SysML parametric model, for assessing the key performance measures of the configurable UAV. In this case, if we go to the UAV block, this is the same parametric model there. You can see what kinds of parametric equations that Sam has defined. First, he has a basic mass rollup equation that is going to compute the mass of this entire configurable UAV based upon the mass of the payload, the mass of the communication subsystems, the mass of the platform, which by the way is coming from Windchill, and other things. It also has a range equation there that relates the range, which is how far this UAV can travel, given the current amount of fuel or the amount of work done by the jet engine, and the mass of the UAV. The other performance parameter he's defined is the max velocity of the UAV, and that has been related to the drag factor on the fuselage and the thrust being produced by the jet engine propulsion system there. And the last one is the endurance. How long can this UAV fly? And that is related to the mass of the UAV, it's related to the work done by the engine, and it's related to the lift provided by the wings. Okay, so it's defined a parametric model to assess some key performance parameters, or given target values of the key performance parameters, work his way backwards to figure out the design variables for the jet engine and so on. And we'll exercise that scenario in both directions. He has created a specific instance of the configurable UAV, which we'll get to here in a second, which is this package, the configurable UAV jet variant instance. And at this package level, you can click on the top level instance element and launch the Paramagic tool. And the Paramagic tool shows Sam sort of an object-oriented structure of the configurable UAV. You can see the configurable UAV instance, so you can see the key value properties, you can see the different subsystems, and if he clicks on the configurable UAV instance, you can actually see all the equations in there. And here, in first scenario, Sam is going to compute the endurance of the UAV, the max velocity and the range, and also do a mass rollup. So those are all targets given the power being produced by the work being done by the jet engine, the drag factor of the fuselage, and the lift in the wings, and the other known elements. So at this stage, he presses the solve button, and that basically executes the parametric model to compute those key performance parameters. In this case, it's using Mathematica as a math engine to solve for those system of equations. And based upon the inputs, what Sam sees is the max velocity of this UAV is 250 kilometers per hour, the range is 230 kilometers approximately, and the endurance is 38 hours. Now, if those given values change, for example, if the mass was updated in the Winchell PLM system, then Slim would be able to pull those numbers in, and the same set of system equations could be solved again by Paramagic for a different set of inputs. And Sam could do that in sort of a manual way like this, or he can set up a trade study using Paramagic, using the user interface, or also use the Paramagic API calls directly from MagicDraw to set up those solving as he goes along. Now, the other interesting scenario that Sam wants to explore is that he's not very happy with this range. He really wants to change the range. In this case, instead of calculating the range, he wants to set that at 250 kilometers. And what he wants to know is what would be the amount of work that the propulsion system would need to do. So he goes to the work property here and sets that as a target. Remember, he has not changed the system of equations. The parametric model is still the same. But because it's been defined in a declarative manner using equations, he can actually change the causality. He can actually try to compute the amount of work that the jet engine needs to do to achieve a given range. He presses the solve button, and voila, it tells him that to achieve a 250 kilometer range, then the jet engine would need to do 163,000 joules of work. Now, as you can see, this would have been very difficult to do with Excel, because in Excel things are pretty much the way we use it, it's pretty causal, and you have to go and change the system of equations if you want to solve it in a different direction. But this is a very natural way that system engineers work. You define the equations, you define the relations, and you want to exercise that model with different causalities. And that's what the Paramagic tool is helping Sam do. All right, at this stage, Sam wants to trigger another detailed analysis, this time using Simulink. So let's get to that. Now, one of the key components of the UAV system, and in particular the platform, is actually the gas turbine, which forms an essential part of the jet engine. And this is a part that is being jointly developed by the platform maker and Sam's team at Get Your UAV. And what Sam wants to do is to be able to do much more detailed and rigorous analysis on the gas turbine subsystem of the propulsion system of the UAV platform. And to do that, what Sam and his team have done is that they have brought in and built here an internal block diagram of the gas turbine subsystem, where you can see now that the gas turbine actually has an air compressor that would compress the incoming air, and it would go into the swirl burner where the fuel and the air mixture would mix and would burn the fuel, and the hot mixture would come out. It would rotate the turbine, which would produce the power, and some part of the power would go back to the compressor to run it through the shaft, and you would also have some exhaust come out. So Sam and his team have defined a very basic flow model using system internal block diagram for the gas turbine. And what they want to do really is, for the detailed analysis, they want to generate a Simulink model out of the architecture model. In this case, the system model, which has this IBD. And they can do that with Slim. Instead of manually taking screenshots of this image or producing documents that are sent over to the Simulink engineers, the Simulink experts, and having them recreate the Simulink model, Sam could really just generate the Simulink model right from SysML and have Slim actually maintain those connections. It would not just be a one-time generation, but actually Slim would maintain the connections. And again, the same sort of things with compare and synchronize as we are seeing with Winchell parts or Team Center requirements or MySQL databases would follow through. It's a very common pattern in SLIM. So he goes back to the dashboard in this case, and then goes to the connection manager tab and selects a file folder, in this case this one, and goes to the structure package here, goes to the gas turbine, and then tries to drag the gas turbine onto this folder in his file system, local file system. And at this point, it gives him three options. Do you want to generate an Excel workbook and a table out of this block? Do you want to generate an NX-CAD model, which we will exercise later on? Or do you want to generate a Simulink model? Those are all possibilities of generating different types of design and simulation models out of the SysML block. And in this case, Sam selects the Simulink model option and clicks OK. And that starts generating a Simulink model from that SysML block of the gas turbine, transporting all the internal structure we saw there into the Simulink model. And this will take a few seconds. All right, so that Simulink model has been generated. As you can see, we can see it here in the Simulink models folder, to which we drag the gas turbine block. If we right click on that gas turbine SLX file and hit open right from within the SLIM dashboard, it will try to open it up in Simulink. Just take a few seconds. And now that Simulink model has come up, and we'll put this side by side with the IBD. And again, this is not organized well in terms of the layout, but that will be an improvement that SLIM has to do, where we could take the layout information from the IBD and lay out the Simulink model. But as you can see, we've got the swirl burner that's being created as a Simulink block. We've got the inputs to the swirl burner. We've got the axial compressor here, which is compressing there. We got the turbine, which is where the hot air mixture from the swirl burner is going out. So a little bit of work here involved to align this. And we've got the power coming out from the turbine that's going back to the shaft. And we also got the outputs coming back from the turbine. So we've got the exhaust here, and we've got the output power here. So all those elements are back in here. Now what you can see, what has happened here is that the architecture model is where the skeletal of the system has been defined, the flow of items on this gas turbine components, and Sam has been able to generate a Simulink skeletal model for the Simulink expert, which is then linked now to the SysML model. And this Simulink model can now be used as a starting point for the Simulink expert to further develop the detailed simulation for the axial compressor, for the swirl burner and the turbine, and do much more rigorous analysis. Another alternative that SLIM could do, which is not shown on this demonstration, is that if Sam would have used Simulink library blocks in SysML, which is possible to do with SLIM, that he could actually develop a full IBD with the Simulink library blocks, and that would generate an executable Simulink model, that one that could be executed right after generation. And so that's another possibility. Either you can create a skeletal Simulink model, which can be further developed and further defined by the Simulink expert in Simulink, or you could generate a fully executable Simulink model. The beauty of this approach is that now the Simulink expert doesn't have to reconcile information coming from the system engineer in documents or other formats and figure out what it meant and what the architecture was, or manually even create the skeleton. We are showing this for a simple model, but if your IBD was complex, it had a lot many parts to it, a lot many flows to it, it does make your life much easy to have that skeletal model automatically generated. And as I mentioned in the usual SLIM style, what's also happened is that the gas turbine now is actually connected to the Simulink model right here. And that is an important part. In fact, the gas turbine is really connected to is a part coming from Windchill whose internal details are being analyzed in Simulink. So you can see that same gas turbine block in the SysML model is actually connected to the Windchill part, gas turbine version A2, and also connected to a Simulink model with the same name, where the gas turbine is being analyzed. Okay, so you can see the power that now we have two connections going from the gas turbine block to two different models outside the architecture model. Okay, the same approach that we showed for IBDs could actually also be done with activities, and Sam could have used that as well. If this model was actually created using an activity model, then even a Simulink model out of that could be generated using SLIM. And that's another possible way of doing it. So you can either represent flows using an IPD or defined flow-based models here using SysML activities and generate Simulink models out of that. Okay. At this stage, Sam is now going to dive into some of the detailed design of the system. And with that, we move to stage 3. Now what Sam has done here is made a little bit of extensions to the architecture model, specific elements in the architecture model, so that he can communicate some basic information to mechanical designers in his team who are working with NX. So the platform part of the UAV, we, in this case, are well aware of the center of gravity of the platform. It's coming from the platform maker, and also a payload volume that has been designated by the platform maker for the UAV, where the Get Here UAV company, the company that Sam works for, will actually locate the instruments in that payload volume. So what we're getting from the platform maker with the platform design is the center of gravity of the platform before the instruments have been placed on the platform in the context of that UAV, and we are also getting the volume that the platform maker has allocated for the different instruments. So we're getting that information, and that is being defined here. We're also getting some important information about the different instruments. So let's take two specific instruments that Sam pulled in from the MySQL database. He also knows about that this instrument, this radar R1, actually has a keep out zone, so which is the volume of the radar instrument plus an area or volume around it, which is where no other instrument should be placed. So there's a keep out zone defined for the radar volume. There's also a keep out zone defined for the video camera volume. Such keep out zones can be defined for all the different instruments. The goal of the mechanical designer who's working with Sam using NX will be to take the payload volume that's been allocated by the platform and to try to place all the instruments in that payload volume in such a manner that the end center of gravity, or the center of gravity at the end of that placement process, and the center of gravity that was originally there before the placement process is not disturbed beyond an acceptable margin. So in this case, what SLIM can help Sam with is that if the feature definitions could be defined here using blocks, then SLIM can help Sam actually seed or generate skeletal CAD models right from the system architecture. And that makes the mechanical designer's life much easier. That makes Sam's life much easier, because again, this information is not being communicated through documents or spreadsheets and not have to be reconciled manually, but it'll be information in the mechanical CAD design model and the system architecture model that will be well connected using SLIM, using the same pattern that we've been showing throughout this demonstration. Okay, at this stage, now Sam goes back to the SLIM dashboard and exposes another one of his repositories, goes to the My Models package, goes to the CAD Models folder, which is empty right now. And on the left hand side, he expands the structure package in SysML and goes to the platform block, for which the center of gravity and the payload volume coming from which has been defined. And what he does at this point is just simply drag the platform block to the CAD models folder, where he selects to generate an NX CAD model out of that block. And that process starts generating an NX CAD model for that platform. This process will again take a few seconds. It's trying to initialize the CAD engine at the back end and then go through the process of generating that part from the information that's available in SysML from the system architecture model. Now we can see that this NX CAD model has been created. You can open it here and this will launch NX. Alright, so we see NX has come up here with that platform part that has been generated. And you can see that two specific features have been generated from the system architecture model. First of all is a platform center of gravity for that part, which is a point, and second is a cuboid, which is a payload volume. What's really interesting to see here is that as this information from the architecture model in SysML has been communicated to the mechanical design model, the part properties have been communicated as the names of features, so they become an important part of the communication between the mechanical designer and the system engineer. They know what features they're dealing with, they know what parts they're talking about, and it's very important to be able to do that. And that's been made possible for SAM through Slim here. Again, we'll try to fit this model to screen and try to show a wireframe version of it. So we can see that that's the payload volume right here, and that's the platform center of gravity. So this is the payload volume that the platform maker has allocated to place all their instruments in, and this is the center of gravity that they have specified at the point where none of the instruments have been placed. This is the center of gravity of the platform. And again, if we double click on this block, I can see the dimensions 2000, 1000, and 1000 mm, which is what we supplied here. Similarly, if we go to that center of gravity point, we can look at its coordinates as well, 1500 and 500 millimeters from the origin. That's what we supplied here. So we can assure that that information has been transmitted to the NX-CAD model. Now, in a similar manner, what SAM can also do is to go to the two other instruments as an example, for which the keep out zones have been defined. In this case, they are the instruments radar 1 and the instruments video camera 1. So you can drag similarly that instruments radar 1 block to the CAD model package and say we want to generate an NX-CAD model out of this. That got there, and similarly the instruments video camera 1. That's generated here, and he can do the same for the other instruments. And if you can open up the radar part that has been created here, you can see that's a spherical shape, and it's a radar keep out. That's the name of the feature there, as you can see here in the SysML model. Similarly, if he goes back to the dashboard and tries to open the video camera part, we can see that's a cylindrical shape. So the actual instrument is there, and this is a keep out zone around it to ensure that no other instrument is placed in that cylindrical volume. Now, the challenge that the mechanical designer is going to have is to be able to go to that payload volume and try to locate all of these instruments in that payload volume. And as I said, what Sam's going to do is, after all the instruments have been placed in that payload volume, the new center of gravity will be computed based on the platform's original center of gravity plus the payload mass. And Sam and his engineers have to make sure that the new center of gravity and the original center of gravity are not far beyond an acceptable margin. So as you can see how we are effectively having this model-based communication, not document-based, but model-based communication between the system engineer and the mechanical designer, really communicating system level requirements as geometry. That's the key part. System level requirements of how big is this payload volume, what is the area around these instruments. That requirement type of information, which mechanical designers always have a hard time figuring out from system engineers, is now right in their CAD model. And again, this has been generated in local file system. These CAD models could have been seeded directly in Teamcenter by Slim as well. Okay, so now we move to the last stage of this demonstration. Sam is really happy with his system architecture model, and what he wants to do is to now seed this system architecture model that he has into his own enterprise PLM system, which is Teamcenter, so that it can be shared with a larger team that is working with Teamcenter, and they can further enhance and develop that product structure, which by the way will be linked to the architecture model. So if Sam wishes to change things and his team refine the architecture, that can be communicated, or they'll be able to pick up changes in the PLM system into the architecture model. So for that, Sam again goes back to his repository toggle window here in the dashboard, goes to the Teamcenter repository, expand this package, this folder here, and selects the configurable UAV block, and then drags it to that folder. And this will start the process of generating items in the Teamcenter repository based on the SysML block structure. And at the end of this process, you can see that a set of items in Teamcenter have been generated from the configurable UAV block and its structure. We can see the cUAV here, and its version A1 has been seeded here in Teamcenter, along with the platform, the communications, the payload, and the software subsystems. And their BOMs have also been generated. In addition to that, what Slim can also do is to actually be able to create trace links between the requirements that were there in Teamcenter and the items that have been generated. The satisfy relationships that we saw in the model between the blocks and the requirements are now being generated as trace links in the Teamcenter repository from the requirement to the item. Again, trace links in Teamcenter have an opposite direction to the dependencies in SysML, but Slim handles that for you. As before, a set of relationships, connections have been created between the SysML model and the Teamcenter items. So for example, if we go to the cUAV block, we now see it's actually linked to version A1 of the cUAV item in Teamcenter, and the same is true for all the other blocks in this architecture model. All right, now we're coming to the end of this demonstration. One of the last pieces of things that Sam is really interested about, which Slim is managing, is get a sense of all the connections that have been created between the system architecture model and all the peripheral models around it. For example, the PLM system models, the database elements, the Simulink model, or the CAD model on the local file system, or potentially could be on a PLM system. He wants to see all those connections. So Sam can see them right in the connection browser of the dashboard, like you can see here. You can kind of expand this package and also filter connections. You can see all the connections for a given element. You can also go ahead and filter connections by different types, by different target elements, by different repositories. For example, if you want to see all the connections to the Teamcenter elements only, or wants to see all the connections to Windchill only, and so on and so forth. Or if you want to see all the connections or rows only that have a connection. So for example, you can use another filter, and now he sees only those rows in the model that have connections. So you can see all the connections in the model organized by the model structure, as you can see in the connection browser. And you can also see a connection summary where you can see a flat list of all the connections. Now this is good, but it doesn't offer that same level of visualization that a graph would. So for this, we have a new component that is made available to Sam through Slim. This is a live dynamic graph that's been generated from the Slim connections, and it's actually a web application that's running on a web browser. In this case, it's Chrome at my end, and it actually shows the different connections that Slim is managing at this point for Sam. These nodes that you see in greenish blue, those are all the SysML nodes. Okay, so for example, we've got them organized by the package structure here, the requirements package, structure package, and so on and so forth. These nodes that you see on orange are the MySQL elements. These nodes that you see here in purple are Windchill elements. These nodes are Teamcenter nodes, and these are nodes that represent elements in the Simulink model or the NXCAD model that's been generated from the architecture model. If you hover over a node, you can actually see all the connections starting from that node. So for example, this guy, this platform guy, is coming from Windchill, but also has in the NXCAD model. And so if you hover over a node, you can actually see all the connections in this very dynamic visualization. You can actually move this around. You can actually change the tension of these connections. You can actually do a search here. So for example, if I search for platform, I can have only those connections highlighted that have the platform element, or if I search for the turbine, I can see those as well. So it's very dynamic, very interactive. And this is the kind of capability that we are working hard on adding to Slim, where engineers like Sam will be able to see all the connections in this dynamic map. Now, some people call this as a spaghetti plate. It looks like, right? I mean, those connections look like spaghettis that are going in different parts of your plate. As these models evolve over time, what would be very interesting to see, how the connections are evolving over time, to view the life cycle of these connections, and do some very advanced model analytics on this connection map that Slim is managing. And that's where some of these capabilities will mature. So on this one, Sam gets a very good perspective on where are his connections. How is the architecture model related to the other models around, whether it's a PLM system or the CAD models. Now imagine that before this exercise, the way Sam was tracking it is perhaps manually in a spreadsheet, because the information being communicated across these different tools was not well defined, was very document centric. Sam was somehow struggling to keep up with these connections and somehow managing them in a spreadsheet and often missing out. So it was a very manual process. But now he can have charts and graphs and plots that could be automatically generated from the set of connections that Slim is managing. So we get to the end of the demonstration, the end of Sam's story. Let's conclude. Sam's mission is really accomplished. From the key things that the challenge problem at the IW had stated, all of those things have been answered here. So let's review them. The first two categories was about showing how software tools could actually help with model development and collaboration for this challenge problem. You can see that Slim is really answering those very clearly. We can have concurrent development happening in multiple repositories, system architecture model being developed in SysML, the part structure being developed in the PLM system, or requirements being managed in a requirements management system, databases of parts that are coming from different vendors and suppliers. And the ability that Slim provides, which is very key here, is the ability to connect the architecture model to these different domain models and to be able to generate models on the other side, to be able to manage those connections, and to be able to compare and synchronize. We are dealing with a multi-repository environment, so we have multiple version management and multiple configuration control systems. This is really a very heterogeneous environment that Slim can manage. What Slim is really helping is to build and maintain this a total system model, which is the architecture model with all of its connections to the different domain models. Slim definitely makes this whole process very usable, very user-friendly, by providing a drag and drop approach to connect models, provide a single mouse click step to compare models and to synchronize models in either direction. It provides smart algorithms at these connection level to be able to compare models and to maintain them consistent as the entire system model evolves over time. There's a great deal of demonstration here about model reuse and use. For example, once the model was built, once that initial architecture was built for the UAV, Sam used parametric analyses and could have done a trade study for the system architecture, computing the key performance parameters like the endurance of the UAV, the max velocity, and the range it can go. For detailed simulation, which is a key part why we develop design and descriptive models, is to be able to do rigorous analysis. We've seen here that beyond the traditional math-based analysis, Sam was able to generate Simulink models out of the system architecture for that gas turbine from an IBD. He was also able to generate NX CAD models of the different instruments with their keep out zones and really able to communicate requirements on the payload volume and on how those instruments would be placed in the payload volume and how the center of gravity would be affected, to be able to communicate those to the mechanical design team. And they are starting from an NX-CAD model that's been generated and not have to recreate it. So communication of requirements as geometry, which was a key part there. And with that, we end this presentation. If you like this demonstration, if you would like to be like Sam, if you would like to use these tools such as Slim and Paramagic in your next project and would like to learn more about SysML, please feel free to contact us. If you have any questions or doubts about any part of this demonstration, feel free to email us and we'll be glad to answer you. Thank you. And with that, we end the presentation.